Hello? Hello? Okay, I think that we can start actually. So we have decided to reduce the gap between two tutorials, so we can start a bit early and finish a bit earlier. My name is Ilya, and now we will have a practical session about reinforcement learning. So it is the last tutorial in this summer school, and I welcome those of you who have survived it. Yeah, you are the most motivated students ever. Thank you. Um, so actually, the lecture was almost 2 days ago, and in this tutorial we will study two topics. First one is the method called reinforce, and the second one is actor critic. So both of them are policy gradient methods. Um, Please open Google Colab of our summer school. You should all have a link to this repository. Okay, okay, that's fine. So open the directory tutorials week 2. So this tutorial has two parts. First part will be about the reinforce method. And let's start with this Jupyter notebook, which is called part 1. Yeah, which is called part 1, okay? So also you can open solutions if you want just to watch and to enjoy. But I want to say now a couple of words what's going on here. This problem, which we will solve with the policy gradient method, is called point-env, and it is a toy problem. It is quite simple. So the situation is the following: we have a point, and point is randomly placed somewhere in the unit square, and the goal of agent is to push this point towards the point 0, 0, right? So it is quite simple, and actions are actually movements of this point. The main complexity here is that we have a continuous action space instead of discrete, so we cannot use some tables. It is harder to find, to do gradification, to find the maximum action which maximizes Q function, for example. So it is exactly the situation where policy gradient methods can be used. Okay, so here is a reward function. It is also very simple. So the maximum, as closer we are to the point 0, 0, the higher is the reward. Okay. You can check the code above in this class point-env. We also have small penalty for actions. So the ideal situation is when point is placed in the center, in the 0, 0, and it does not move. Okay? Okay, so we will solve this toy problem with the reinforced method. So what this method is about, it is based on the log derivative trick, and I recommend you to learn this trick if you have not done it yet, because it is very useful not only in reinforcement learning but in some other applications of machine learning. So this trick allows us to calculate the expected value of some function. Here is Q function, and they calculate the gradient of this expectation over the parameters of the distribution. So here the distribution is a pi function, is our policy, and it depends on the vector theta. So instead of analytically calculating gradient over this policy inside the integral, we can use log derivative trick. So So maybe in detail this trick is explained in lectures, but in a nutshell, what we are doing here, we need to sample. So we need to calculate the Monte Carlo approximation of this gradient by sampling points, and then calculating average of the gradient of the logarithm of policy. Okay. So, and it will be a noise approximation of the gradient of the expectation itself. Okay, so now we are working with the reinforcement learning problem, and the sampling from integral, it means that we allow our agent to play its game until the end. So we play several episodes, and we want to maximize the expected return, as you remember, I hope. Okay, so then we obtain the following equation. So the gradient of the expected return is the Monte Carlo estimate, and we need to calculate the gradients of the logarithm of the policy. Okay. Okay, so the first problem here is to implement this method, which is called reinforce, for the problem I have described above, which is called point nth. Okay, so we have Gaussian policy. It means that our action is distributed, it is normally distributed, and the policy depends on the matrix 2 by 2, which is called theta here, and we have two-dimensional state. So what is state here in this problem? Anybody follows my idea? So we have point on a two-dimensional plane, and the state is what? So it's coordinates, right? Yeah. Okay. So if we have these two coordinates, the solution is quite obvious. We should move right to the center, but let us allow our agent to learn this policy. Okay, so here is the first exercise where you should calculate the mean action, the sampled action, and the gradient of the logarithm pi. So if you maybe you can spend several minutes, try to do it yourself. Okay, so any progress? Anybody finished? Anybody's actually trying to do it? Okay, guys, you're the best. Breathtaking. Um, okay, so maybe I will type some solution here. So the mean action, it is just mean of the two-dimensional normal distribution, multiplication of theta by state, theta matrix by state vector. Um, so sampled action, it is the same. It is mean plus dispersion, right? Plus standard deviation. So if you are going to calculate the gradient of the logarithm by yourself, it is also not so complicated, because the term with determinant, it disappears when you the gradient of logarithm, it is gradient of function divided by the function itself. So the most complex part of normal distribution with determinant, which everybody forgets always, it disappears. Okay, and we come to this solution. Okay. Okay, we can proceed further. And the next idea, which was explained during lectures, is reducing variance. Maybe I here it is better to show the lecture itself. Oh, because it is open here. So it is also very interesting idea. Where is it? Reducing variance, and it is used not only in reinforcement learning but in other places in ML. Consider two random variables x and y, and our goal here is to estimate the mean value of x. So how to reduce the variance of this estimate? If we have another variable y with known mean, we can subtract from x this second random variable y, and if these random variables are positively correlated, hopefully the noise will disappear when we subtract one variable from another. So the mean of such equation is the same, so the mean of x prime is equals to mean value of x, but the variance is lower. Maybe you are familiar with the optimization method, which is called SVRG, stochastic variance reduced gradient. Yeah, SVRG, and it is based on exactly the same idea, how to reduce the noise of the stochastic gradient. Okay, so it is just an interesting method. Maybe you can read it further after the lecture if you want. So what we do here in reinforcement learning, we subtract from the reward the value function and reduce its noise. So we make our gradient, the gradient of the policy pi, less noisy by reducing its variance. Okay, so we need some regression for the value function, and in this task we have here a set of features which are function of states, because the value function depends on the state, right? So the problem here is to implement this regression and to use it. Okay, so please do it. So here we have already features. It is FT matrix, and we have targets. Oh yeah, I missed to say, you can implement here just a simple linear regression by minimizing mean squared error. Okay, for this problem, we can use the built-in function from the NumPy, which is called least squares, and the prediction for a linear regression, it is inner product, it is dot product. Okay, now we have a baseline, which is a value function. Okay, and finally we can run our agent. Okay, so it takes some time for agent to learn, and we can start now to solve the second part of this practical session. Okay. Okay, so please open the notebook in Google Colab Reinforcement Learning 3, Part 2. Okay, so now we will solve a more interesting problem, which is called the pendulum problem. It is from the OpenAI Gym, which is a framework for evaluating reinforcement learning algorithms. So let me show you the video about the pendulum So what's going on here? We have a pendulum, and it is based on the physical model by gravity and no friction. The agent can rotate the pendulum clockwise or counterclockwise, and the goal is to preserve the pendulum in the upward position. Okay. Okay, so the action space here is the force by which we rotate pendulum clockwise or counterclockwise, and the state is two-dimensional, is its angle and the velocity. Okay. So we are going to solve this problem with the actor-critic method. Okay, so first we have here some definitions of classes and functions. So for simplicity, I have included them directly in the notebook to prevent possible errors. Okay. Okay, it should be okay now. Okay, and we are going to solve this problem with the deep actor-critic method. So it's better to open the lectures, and here is a nice explanation of actor-critic. The equation at the top of this slide is the reinforced method when we use actual rewards from environment to calculate the gradient of our policy. So the problem with this approach is that we should wait until the end of the episode to obtain the reward, right? And alternative method is called actor-critic, where we replace the return RT, capital RT, with the Q function, because it is the same in expectation. And the Q function is available for all states. So we can not it is option that we can do learning without waiting to the end of the episode. So on the other hand, it is easier, and on the other hand, it is harder, because now we need to build two regressions. First regression for the pi, for our policy, and the second regression for the Q function. Okay, so and the explanation here is that our agent makes some action, and a critic gives some immediate feedback on this action by Q function, so by estimating the quality of this action. Okay, so let us return to the Colab. Here are the equations. So we have two sets of parameters. The policy pi depends on theta, and Q function depends on omega. We also are going to reduce the variance by subtracting the value function, similar to the way we did in the reinforced method. And another trick which improves reinforcement learning is encouraging exploration with the entropy. So here in the integral, we subtract the logarithm of policy, so that pi multiplied by logarithm pi, it is entropy. So can anybody explain what is your intuition, why addition of this term encourages agents to do more exploration? Any ideas? So pi, it is a given state. Pi, it is a distribution over actions, right? So it is a probability distribution. And pi multiplied by logarithm pi, it is entropy. Okay. So how entropy term helps us to do more exploration? Any ideas? Imagine a probability distribution for simplicity, discrete probability distribution, and when the entropy of this distribution is maximal. What? Yeah, equal probability for all choices, right? So it is point when entropy is maximal. And here, this is exactly the case. So we are pushing the gradient to the direction where where the distribution of action is closer to uniform. Okay, so we prevent the collapsing of this distribution. Okay. Uh, um, Actually, yes, but here we do not do it. Okay. Okay, so this code is based on PyTorch. So luckily, we do not need to calculate gradients ourselves. Here is actor critic. Okay, so the problem here is to write equations for the advantage function, which is the difference of q function and value function, and the policy loss. So please spend a couple of minutes, try to understand the code and to type some code here. Okay, so just we need to transform this last equation to the PyTorch code. Okay, so here is the solution. Oh, it is not solution. Okay, so advantage function is just the difference between q function and the value function. Okay, so and policy loss, it is I showed it a minute ago. It is this equation. Uh, so one question for you, if you follow me, why we need here to call the detach method for the advantage function? So in PyTorch, calling detach means that we do not calculate gradients, right, for this tensor. So you remember that now we have actually two neural networks. First, neural network which is regression for policy, and the second neural network for the advantage function. So policy loss, yeah, it depends on theta, not omega, and advantage function depends on omega. Okay. Okay, so actually I forgot it, but we started first agent in the point tense environment, and in my collab it is finished. So this notebook produced a interesting plot. It is average returns with different discounting factors. Okay, and we can conclude here that the best variant is no discounting, actually, with discount factor 1. Um, so it is not usual because typically using discounting factor less than 1, it helps to reduce the variance of our gradient, but in this case it is not the case. Okay, so this problem is solved, and we can return to the pendulum problem. Okay. Okay, so we can skip the last problem here, and we can already run our agent. Excuse me? Yeah, it is like hyperparameter. I think that missed something. Let me check it. Okay, maybe run this cell again. Helps. No, this is it is other exercise. So I hope that it will run without this line. Probably. Okay. Okay, so we see here that average return it do increases. So our agent learns something meaningful. Um, it is quite close to zero, at least closer than in the beginning, in the first epoch. Okay, I think we can stop it. Um, so the algorithm it actually works. And the last exercise is to implement the reparameterization trick. Um, Actually, it was not described during lectures of Professor Whiteson. So the idea here is that instead of sampling from policy itself, we can sample from some artificial distribution. Here we sample random variable from zero mean normal distribution with the unit standard deviation, and then transform it with the hyperbolic tangents function to the action. Um, so of course it is trick, and we have not proof that it will converge, but in practice this trick reduces the variance of the gradient and leads to faster conversions. So probably I will just solve this problem myself because it was not described. Okay, so here is policy loss for the reparameterization trick. Okay, run this cell again. Okay, so we can notice here that that our return became something like minus 500 at 11th epoch. So let's check um, how how fast our agent will learn using the reparameterization trick. Okay, so let us check. Maybe I have missed something. Nope. Seems to be okay. So for me, as I see this number, the agent learns with the same speed as without the reparameterization trick. So um, maybe maybe we should use some lucky seeds to prove what I explained before. But in any case, you can try this trick in your practice, and it often leads to faster conversions. So you see that reinforcement learning is quite empirical science with lots of hyperparameters, and it requires some luck maybe. Okay, guys, any questions? Here, which subscript? Sorry. Omega, it is parameters of the advantage function. So it is parameters of neural network which predicts the advantage function given state and action. Right. So in the code, actually, we update, of course, both theta and omega. So we do two backward passes here. So Q function loss backward and value function are separated, and policy loss backward. Okay. So yes. Because the exercise here was to type only one loss, so of course losses for the advantage function, this loss is also calculated and optimized. Okay. Other questions? Okay, thank you. Thank you for your attention.